What was the purpose of writing this book, Wild Dreams?
The purpose is to inspire young people to get into natural science. And this because at the moment recruitment is not too good in all the Western societies, and we are worried about whether we at all get candidates for the big research in future. So this is the first thing. The first thing is to write a book that can inspire people, because it gives some of the wild ideas. Why do we mix up all these biomolecular things together with galaxies and black holes? And seemingly these are very different things. But they are not, in a sense that a lot of the techniques and methodologies to describe one of them is also the one that can be used for the other thing, and therefore they have inspired each other. So this is first. The second thing is that many people would say that the greatness of all this space-time curvature and so on, all these things that we would like to find but actually not have seen, wormholes and so on, they are actually in a lower dimension. They are inside the cell, and this was a surprise to me.
You say the universe is in the cell, or what?
Yeah, the cell itself is a very big universe, and to consider if some proteins that we have studied very much, and I describe very much in the book, a protein in the cell is something like a solar body, a star in the galaxy. The thing to study is proteins, because we understand their atomic structure, and they are on the mesoscale of complexity. While if you take the cell, it's a completely kind of different thing. Exactly like stellar dynamics is very different from galaxies. Everybody will say it, because, and therefore one is a very good example of the others. So therefore you ask, secondly you ask, have you found any of these weird topological things that could appear as, or they are partly seen in the solutions to Einstein's field equations. So, and this has inspired me very much in looking for it in the biophysical field, and especially in the cells. And therefore, in the cell there are a lot of canal systems that facilitate movement of proteins from their construction and from their birth, you can say, in the ribosome out to the edge of the cell. It's a huge travel, and it's something that you will hardly see a star is doing throughout the galaxy. But actually there are, I understand, there are quick runners also among the stars. But it is certainly a thing seen in the cell, and it's important with some topology like the Golgi apparatus that has a lot of wormholes, you can call them. And then Holger, are you there? Holger will say that three-dimensional space, taking aside space-time, but just having three-dimensional space, then two-dimensional surfaces is a kind of trivial thing. Holger would say, but not so trivial, because still you have a very big description of the cell membrane, which is very famous for topological phases, and a thing I have studied myself very much, and I'm very happy to that Holger agreed, if you have agreed, that to include these chapters in the book, because the chapters are about topology. Some research I did with some colleagues, John Ibsen and Sten Markvarsen, and this is things that in America they consider it quite a very fine science, and actually we also got it out here 10 years ago, and it is science about using differential geometry and things that you have usually seen in space-time, I mean, typical things for the universe. These things we have employed for the cell membrane, and many people have done differential geometry, but not the Gaussian, not just the mean curvature, and they are two different things. So I'm very much into the Gaussian curvature, and there Holger would say, well, that is kind of a trivial thing. It is just the Euler number. It just it's just a characteristics, but still, it turns out that it's very much the evolution of life, where you first have one single cell, and then it divides up into many small cells. It's very important with the pH value and the phase diagram there of topology, because the Gaussian curvature, the coefficient of the Gaussian curvature, is changing very much through the first stages of life.
What is the book describing about life?
Yeah, about life. The book is describing the elements of life seen in atomic constituents. And then it is the necessity of quantum calculations in the life processes. And many people have been very skeptical in Germany. I have discussed very much with people that don't really, to many people, all this Heisenberg and uncertainty relations is a very sacred thing. But I must say, also with Heisenberg's family, I've discussed it, and it simply turns out that the function of proteins in the life processes, that can only be understood in terms of quantum mechanics. Electron transfer is an essential thing. For many proteins, a tunneling process is a very important thing. Let me give one example, and I think I also we mentioned it in the book. Alcohol dehydrogenase has people discuss, but this is the breakdown of alcohol. It's a very important thing in the liver of our body, and for the wine and beer industry it goes the opposite way. It builds alcohol from sugar. We know that from the fermentation, and that is an essential thing, is the quantum mechanical, the tunneling. In the case of breaking of alcohol, it is the hydride H minus tunneling through. It is yeah.
Okay, so that is a very controversial issue.
Yeah, it is,
because you're actually saying that life is atomic structure. More or less. Maybe I'm wrong.
Yeah, the chemistry is exactly as we discussed before here. The chemistry is is really nuclear coordinates. I mean, where is this alcohol molecule, and where is that, and where are the enzymes that are arranging these decomposition or these processes, and therefore these things are given, of course, by the molecular coordinates that are again given by the bulk chemistry, the nuclear coordinates. But then there are the electronics, and therefore people will there really be very
because neuroscience says that it's electricity firing in the neurons, but you're saying it's quantum.
Yeah, there are some
explain that.
Yeah,
what does the book say about that?
Yeah,
that is very interesting.
Yes, it is. There are some things, and Holger has kind of seen that thing. We have discussed it with Thomas Heimburger. He says that it is just solitonic. You can say they're also quantum solitons, but classical solitons that are the signals in the nerve system, and there we would rather say classically and or in a conservative wisdom, we would say that it is opening and closing of ion channels. That is the essential thing.
Where is the ion channels?
The ion channels sitting in on the axons, sitting on the surface of you can say of the nerves, of the nerve fibers. Coming out from the...
But we have nerves everywhere. So
we have nerves everywhere.
Is it going on in the brain, or is it going on everywhere?
It's going on everywhere, actually.
Please explain that.
No, but it's. I'm not a physiologist, but I would say that some of the biggest nerves goes from your spine, all the way down, or from the brain down through the spine, all the way down to your big toe, and this is one axon. It is beautiful, and this is then filled with ion channels, and some people will say this is solitonic, fast transport. And okay, so there are different things, but anyway, if it is opening and closing of ion channels, then it's very much quantum mechanical calculations that are needed. And wouldn't you say that, Holger? But now it is a controversial thing. Many people at this point, many people at his institute would say that. That it is perhaps some classical solitonic equations. Some chapters of the book is models of the brain, and this is neural networks, and this is random neural networks, and it is nerve fibers and so on. All these things are also described in the book, so it's certainly of interest whether it's one mechanism or the other mechanism. And also the synaptic, the whole synaptic processes are also very important, and actually also described in the book. The book is so that it is the first part of the book is classical and more first conservative and then more wild dreams and so on. But all the big calculations that I didn't want to avoid, they are pushed to some appendices, and I'm a little bit sorry, but this is a whole bunch of. It is a kind of. It's a little bit of a mess because there are so many formulas, and even to. But I think people will still enjoy it. They can just read the first half of the book, And if they want to have something in details, say of the typical chapter of Holger, one of them of string theory, then they can go to the appendix of string calculations, and hopefully they will be satisfied with some of these equations.
What is the difference between life in itself and consciousness? Do you at all talk about that in the book?
Yeah, that's a hard thing, because many people are, and I just pushed in, or we Holger, we took certainly a little bit controversial. We took some pages from some project description that we have been used for getting some money, and this has a little bit to do with you can say consciousness, but this is a little bit dangerous word in itself, because how exactly to define it. But it is true that we have used something, the structure of microtubuli. And this is the cytoskeleton, and this is also, in that sense, many people are talking about quantum mechanics and so on in that respect, and therefore they have spoken against this this consciousness, because quantum mechanics will be too much fluctuation. But then you have a new concept. I've just mentioned it. We have, Holger, I hope that you agree that we have mentioned this thing called quantum protectorate. And the quantum protectorate is something that could guarantee some islands of quantum behavior without interference from the that will destroy these quantum behaviors, and this is something that has been used in condensed matter theory, and I have not myself really created anything here. I used what the literature has proposed, but we have just mentioned it. So that's kind of interesting thing. I still I myself have concentrated more on the physical, on the biochemical processes.
If biochemistry is in the bottom of the atomic, sort of, if this is something happening on the atomic level,
but, okay.
So if life is there, already, then it's also here.
Yeah, I would not call it a bottom, because this is molecular, of course. But you're right. Important of the molecules is, of course, the bonding. Mm-hmm. And the bonding, the ability to create bonds and so on, say, for instance, hydrogen bonds, it is a key element in the catalysis and in life processes. Definitely. And for instance, we talked before about alcohol dehydrogenase, but we can also talk about basic proteases, I mean, what is called digestion. And this is proteins cleaving up, or enzyme proteins cleaving up other proteins, or cleaving up other biomolecules. And this, of course, is a very important thing in the body, or in the cellular processes. So therefore, so we talked about biochemistry. This is biochemistry. Mm-hmm. But I mean, quantum aspects are very important in biochemistry, even though most of the calculations done today are classical molecular mechanics, I would say, and this is gigantic compilation or gigantic processing, computer processing of a big amount of Newtonian equations of motion. Is a huge thing, and often we end up in a picture, and that we have also described, where a protein is sitting like this, so you don't have a frozen structure, but you have something you can say that are alive by this. The functioning of the protein is very much enzymatic processes. So I think we used in a chapter we mentioned Einstein's one of his great articles, which is continuation of his Brownian motion article, is about a protein. He didn't know at that time. He called it schnelle enzymatische Prozessen, but this is exactly the difference between, you can say, classical binding, where the molecule, the protein for instance, is frozen, and the one where it is enzymatic, and therefore Einstein has an entropy formula that is a very important thing that we mention. We made this book with all these incredible, a lot of details mixed up together, and many people will get a kind of bad feeling for that, and that's also true. But on the other hand, we brought things together that we can say we have helped to nurse fields of physics, modeling models of physics that we have helped. But just helped, I mean, in all modesty, it's a lot of big inventions, a lot of great people that have are the main actors, you can say, in this field. But we have helped making something, and this is a lot to do with fantasy, but also a lot to do with mathematics. It's not just fantasy. So we want to bring up these ideas. Some of them are truly crazy ideas.
Okay, what is your most crazy idea?
Oh, but the crazy idea is, one is Holger's idea about God allowing catastrophes or not allowing it. The complex action thing is a kind of wild idea.
That was Holger's crazy idea. What is your crazy idea?
What is my crazy idea? Oh, my crazy idea is a whole world before Big Bang. I mean, it's a whole world of what I call luxons, I mean, light particles, so another photons, and many people are disgusted with it, but I have simply taken the metric and split it up into submetrics. Or the metric explained, the basic metric explained by subparticles. It's a little bit crazy idea, but and this is several people have also come up with that. Teresawa, I think, is one, and so therefore we are not so outstanding that it's never seen. But then comes some of the more brilliant ideas. I would say the Holger's idea about using an opposite Einstein, you can say, of protein dynamics, protein folding, that put all the metrics in the kinetic term rather than in the G metric in the G functions, the Riemann G functions, to put them in the kinetic rather than in the potential energy. This is a kind of a great idea, because then protein folding then becomes a matter of, you can say, string between, or distances between side chains. And one thing, once one is curling up, then it has complete influences on other parts of the protein in a kind of metric way. So there was there was another idea. So then comes as our quark stars. I mean, this is there are a lot of superconductivity and a lot of magnetic fields that are sitting like sitting on top of these and magnetize is also a thing. Some people said
what
they
was
have
that? Magnetar, what is
yeah,
that?
it's not avatar. I mean, it's magnetar is magnetic quark stars. I mean, it's something is speculated, and I was very happy when I suddenly saw it on the internet. But people have pulled it back again. I don't know if it's, but some people want to be. Probably want to be famous for that, but at least we give the equations.
What is the future of physics,
Oh, yeah.
theoretical physics?
Yeah. Unfortunately, it is partly super big groups of hundreds, thousands of postdocs or PhD students that are working on these mega projects, and it's a little bit of pity, because perhaps it could have been more, it could have been better for fantasy that a lot of young people are setting themselves with crazy dreams in their in a room on the top floor in the city in a city of in the west or in the east for that matter. So I think that with physics today, people would like to hear crazy dreams, but they cannot follow them because simply there's not enough money. Funds money are given to quick money-made solutions of and quick business, and it's hard to follow crazy dreams. Yes.